It's time now to move to Luca Razzoli. Are you with us, Luca? Yes. Hello.
Yes. Hi.
Let me say a few words about Luca to introduce him. So Luca, he graduated in 2018 in the University of Modena and Reggio Emilia. Then in the same university in 2022, he got his PhD under the supervision of Paolo Bordone and Matteo Paris. Currently, he is a postdoctoral researcher in Insubria University with the responsible scientist Giuliano Benenti. Today, he will talk about the dimensionality reduction method for continuous time quantum walks. Please, Luca, you can start.
Yes. Okay. Can you hear me and see the screen?
Very well and clear.
Okay. Thank you for your kind introduction and for this opportunity. So this is the brief outline of my talk. So in the first half, we will review the main and the basic concepts and the features of classical random walks and those of quantum walks. Then in the second half of the talk, we will focus on the dimensionality reduction method for continuous time quantum walks. And then we will discuss a couple of examples where this method can be of use. So let's start with the classical random walk. For simplicity, we focus on the random walk on the line in which the walker has the same probability of jumping to the left or to the right. And give me a second, because I need the pointer. Anyway, so this random walk can be implemented also in a Galton board. A Galton board is a vertical board where at the top you have a box with several beads, and then when they start falling down through these pegs, they randomly scatter. So we collect them at the bottom, and each slot corresponds to the final position. And what we observe at the final step is that we obtain a binomial distribution of the beads in position space. So from a different point of view, we may say that the classical walker at each time step tosses a coin, and depending on the outcome, head or tail, it moves to the left or to the right. But what if it could use both head and tail at the same time? Well, this is the principle behind the quantum walks, because we can exploit the superposition principle. In a quantum walk, we have two quantum systems, the walker and the coin, but these can be also different degrees of freedom of the same particle, such as position and spin. Even in this case, we consider the one-dimensional case for the position space, and so the coin space is two-dimensional, spin up and spin down. The evolution is defined by the single-step evolution operator, which comprises two operators, the coin operator and the shift operator. Then the evolution is obtained by repeatedly applying this operator to the initial state, and then the probability is obtained by summing the squared moduli of the probability amplitudes. So just to give an idea of how this step evolution operator works, we consider, we suppose that at a given time t, the state is with the particle localized in position space with the spin up. Then we apply the coin operator to the coin state. So we are quantumly tossing the coin state in order to obtain a superposition of spin down and spin up. Then we apply the conditional shift operator, which makes the state propagate depending on the coin state. So if we repeat this step for the next time step, we see that these two states will propagate also to the same position. So the wave function will undergo self-interference effects. In the next example, we may focus on the Hadamard discrete time quantum walks. In both cases, the walker is initially localized at the origin of the infinite line. But in this case, for this initial coin state, we obtain a final probability distribution which is asymmetric. So there is a bias, a directionality in this work. Instead, if we consider a different initial coin state, we can obtain a symmetric probability distribution. So if we want to compare classical and quantum works, now we consider the symmetric case, a classical worker can explore one path at a time, while the quantum worker can explore multiple paths at the same time. Then a classical worker will be distributed according to a binomial distribution with a maximum at the origin, so the initial position. Instead, a quantum worker will be distributed according to a probability distribution which shows local minima and maxima due to the self-interference effects. Moreover, the global maxima in the quantum case will be well far apart with respect to the initial position. Moreover, a classical random walker spreads diffusively, meaning that the variance in a position space is proportional to time. Instead, a quantum walker spreads ballistically, so the variance is quadratic time. This means that a quantum walker spreads faster than a classical walker, and this is the reason why quantum walks are widely used in developing quantum algorithms, for instance, to achieve speed up with respect to a classical analog of the algorithm. So a few remarks. If we measure the particle position after each time step, then we obtain a classical random walk, because at each time step, we destroy the correlations between different positions. So in order to observe the peculiar features of a quantum works, we need to perform the measurement only at the end of the process, or at least not after every single time step. Randomness. Unlike the classical random walk, a quantum walk is a deterministic process because we know the state of the system exactly at any time. However, randomness is the result of either the coherence or measurement processes that we can perform either on the quantum walker or the coin. About the quantumness, well, superposition and interference are not specific of a quantum system. So we may simulate some properties of a single quantum walker by means of a classical physical system. However, a quantum mechanical description is needed to account for the complementarity of the single quantum walker, I mean the wave-particle duality. Moreover, if we include more walkers and coins, we can have entanglement, so non-classical correlations in the system. So this was the discrete time model, and a few years later, with respect to the discrete one, the continuous time quantum walk model was introduced. In this case, there is no coin, and the prototype of this model describes the propagation of a quantum particle having kinetic energy when confined to discrete spatial position, so a graph. A graph because vertices are the allowed position, and the edges represent the possible transition between these vertices. From a mathematical point of view, the graph is represented by the Laplacian matrix, which is a real, symmetric, and positive semi-definite. And here is an example. And along the diagonal elements are the degrees of the vertex. So, for instance, the vertex has degree 6 because there are 6 edges that are incident to the first vertex. Then the off-diagonal elements are related to the adjacency matrix, so 1 whenever the 2 vertices are connected by an edge and 0 otherwise. We use the Laplacian matrix because it is the negative discrete Laplace operator on a graph, so it is an approximation of the continuous Laplace operator, of the negative continuous Laplace operator, which is we can obtain by finite difference methods. For instance, in one dimension, we can see that these two operators, the approximation of this operator in the Laplacian matrix, are equivalent except for a constant. So indeed, the Laplacian matrix plays the role of the kinetic energy. So again, a classical random walk is described in terms of probability, which evolves according to this differential equation. And in order to have a valid probability conserving classical Markov process, the matrix M must satisfy this condition. On the other hand, a continuous time quantum walk is described in terms of probability amplitudes, and this must satisfy a Schrödinger equation. This matrix, say the Hamiltonian, must be Hermitian in order to have a unitary quantum process. The Laplacian matrix satisfies both these conditions, so it is useful when we want to compare classical and quantum walk in the continuous time model, but instead the adjacency matrix can only generate a quantum walk because it does not satisfy this condition. So in general, any Hermitian operator which respects the topology of the graph can generate a valid continuous time quantum walk. Quantum walks have several applications ranging from quantum computing and quantum algorithm to the modeling and simulation of other physical phenomena, including coherent transport on networks. So now we move to the dimensionality reduction method for continuous time quantum walks on graphs. In most of these problems, we are not interested in reconstructing the whole probability distribution of the walker, but we are interested in population in a specific node of the graph. The graph often has some symmetries, so this implies that actually the dynamics of the walker that we need is restricted to a subspace which is smaller than the full Hilbert space that is spanned by the nodes of the graph. As an example, in a spatial search algorithm, we start from the equal superposition of all the vertices, and we are interested in maximizing the probability at the solution node. Another example is the exciton transport to the reaction center in biological systems, where the typical figure of merit is the transport efficiency, which is defined as the integrated probability of being trapped at the reaction center in the limit of infinite time. So even in this case, we are interested in the population in a specific node. In this method, it is commonly assumed that the Hamiltonian is time independent. So we can Taylor expand the time evolution operator in this way, and then we can write the probability amplitude at the node we are interested in this way, where we are considering a reduced Hamiltonian and a reduced initial state. P is the projector onto the Krylov subspace, which is defined as the subspace which is spanned by the states obtained by iteratively applying the Hamiltonian to the vertex state of interest. So this subspace is the minimal subspace that contains the vertex of interest, and it is invariant under the unitary evolution generated by the Hamiltonian. So the idea is that if the graph is symmetric, then there will be only a small number of linearly independent states in this subspace. So the key point of this method is that it provides a reduced model that it is simpler, but it still fully describes the dynamics which is relevant to our continuous problem. In particular, it maps the original continuous time problem on a graph to an equivalent continuous time quantum walk on a line where the edges are now weighted and the vertices are representative of the basis states of this invariant subspace. So now I will discuss a couple of case studies where this method can be effectively used. So we start by discussing coherent quantum transport. So we consider a continuous time quantum walk on the graphs in the absence of decoherence and without disorder. So we only include the trap vertex, which is responsible for the continuous time loss processes. So we can phenomenologically model this process by considering this non-Hermitian Hamiltonian. So it generates a non-unitary evolution because of the loss processes we have at the trap vertex. So under this assumption, so no disorder and no decoherence, it is possible to show that the transport efficiency, which is defined in this way, can be conveniently computed as the overlap of the initial state with the Hamiltonian eigenstates that have a non-zero overlap with the trap vertex. Why this? Well, if we define the subspace lambda, which is spanned by these Hamiltonian eigenstates, then we can expand also the initial state in these two subspaces, so lambda and this complement. So we see that in the limit of infinite time, all and only the components within this subspace will be absorbed by the trap vertex. The others will be preserved. So we can see that in order to compute the transport efficiency, we need to diagonalize the Hamiltonian because we have to know the eigenstates that overlap with the trap vertex. However, it is possible to show that the invariant subspace that we compute with the dimensionality reduction method is indeed the same subspace that we need to compute the transport efficiency. So if we use this method, there's no need to diagonalize the Hamiltonian, which in general might be difficult. So in this work, we have investigated a purely coherent quantum transport modeled by continuous time quantum works on graphs with the purpose of investigating whether there is a possible correlation between the connectivity of the graph and the resulting transport efficiency for the worker. So we have considered different graphs having different regularity, symmetry, and connectivity. And we focused in this slide only on localized initial states. So we see that if we plot the transport efficiency against different measures of the connectivity of the graph, well, yes, we can observe a specific correlation for certain graphs, but in general, we cannot say that the transport efficiency and the connectivity are correlated. So we conclude that connectivity is a poor indicator for the transport efficiency, as well as the regularity and the global symmetry of the graph. A few remarks. Once we have the invariant subspace that we need to compute the transport efficiency, then we know that any state which is, belongs to this subspace will provide the maximum transport efficiency. However, on the other hand, if we consider a state which belongs to the complement, to the orthogonal complement of this subspace, then it provides null transport efficiency. And this might be of interest when maybe in your network you have a defect which causes loss processes and you're interested in preserving your excitation in the graph, in the network. Moreover, it is known that removing an edge in the graph, so in a sense we may say that breaking some symmetries of the graph, can improve the transport efficiency. However, in doing so, we are somehow changing the topology of the graph, so we are creating defects. So in another work, we have investigated the possibility of enhancing the transport efficiency, but without changing, without affecting the connectivity of the graph. And we can do this simply by adding some complex weight to a few edges. And I want to stress that this approach for a specific choice of the parameters generalizes the edge removal. So as an example, we can see how this approach works in the complete bipartite graphs. So for the unperturbed graph, we see that the dimension of the reduced Hilbert space is 3, and we have a low transport efficiency for localized initial states. So here in the first subset of vertices, and this one for the other subset of vertices. However, as soon as we perturb just one edge, we see that the dimension of the reduced Hilbert space increases, which is indicative for us that of the fact that we are breaking some symmetries of the graph. And we see that, for instance, in this case, just by perturbing the edge connecting the vertex L to the M1, we are able to achieve a unit, which is the maximum transport efficiency for both the edges, for both the localized state, independently of the value of the parameter lambda and theta. Similarly, this works in a complete graph, so in the fully connected network. But in this case, we also see that if we perturb two edges, then we can play on this phase in order to achieve a unit transport efficiency for an initial superposition of two localized states. However, this approach doesn't always work, as in the case of the star graph, where the trap is the central vertex. We see that in this case, even if we perturb one or two edges, the reduced Hilbert space is always dimension 2, and we are not able to achieve unit transport efficiency. What is interesting here is that when the trap vertex is the central one, which is the fully connected one, so it is adjacent to all the other vertices, then we obtain the same results that we have in the complete graph, where all the vertices, where there is our all-to-all connectivity. And this is just one of an example of a more general result that we have proved in this work, which is the universality of the fully connected vertex in Laplacian continuous time quantum walks. Universality because this result is independent of the graph considered. So the reason is that whenever we consider the continuous time quantum walk generated by the Laplacian matrix for the fully connected vertex, then we always end up with the same invariant subspace and the same reduced Laplacian matrix. What I want to stress is that this result is specific for the Laplacian matrix because it is not true if we had used the adjacency matrix. Then this result, this universality, generalizes also to Grover-like continuous time quantum walk. Grover because in the Hamiltonian we include an oracle Hamiltonian, so a projector onto the fully connected vertex. And as a result, this means that we can generalize to many other graphs all the results that we already know for the complete graph. As an example, the spatial search of a vertex is optimal on any graph when the solution node is the fully connected vertex. So this means that we are able to reach the solution node with certainty in finite time, just like in the complete graph. Similarly, if we consider the coherent quantum transport, then all the graphs where the vertex is the fully connected vertex inherit the result we know for the complete graph, so a transport efficiency which is 1 over the number of vertices minus 1. So to conclude, many problems can be formulated by continuous time quantum walks on graphs, and the dimensionality reduction method provides the tools to exploit the symmetries of the graph in order to obtain a reduced model that still fully describes the dynamics that is relevant for the original problem. In this talk, we have presented a couple of examples where we have employed this method to solve the problem. In particular, we have discussed the transport efficiency of continuous time quantum walks on graph, so a purely coherent transport, proving that the connectivity is a poor indicator for the transport efficiency, but also that just by minimally perturbing the graph, we can improve it. And on the other hand, we have proved the universality of the fully connected vertex for Laplacian continuous time quantum walks. And I think I'm on time, so I thank you for the attention.
Thank you, Luca. And now let's wait for some question, if any. Meanwhile, let me ask one, which is probably trivial one, but in the case of the star graph, the fact that you cannot increase transport efficiency by changing a link is trivially related to the fact that you are forced to pass in the center if you want to move, or is something more complex?
Well, in a sense, yes, but we may also expect that that starting from an outer vertex, then when the trap vertex, which are forced to pass through it, then we can expect that in the long time limit, then the excitation will be always absorbed at the end. But this is not the case. But
okay, maybe the question.
I don't know how to.
Okay, you know, I'm classical minded, so it seems to me that you have to pass there, and this makes a sort of constraint with respect to the case where you have many possible paths. But I don't know, this was just a curiosity. Okay, is there any other question? I don't see any. If not, we meet again for those of you which will be willing to come. Next seminar will be in January. So thank you. Let's thank again the speakers. And bye-bye, everyone.